Hello, and welcome to episode 1 of Information Theory with me, the Mad Coder. What codes at midnight? Take a little sip of coffee and get started. Now, it's my plan to teach you the philosophy of programming. And on my particular philosophy of programming, now, all programming involves data and data transformations. So a data transformation is a kind of a construction in which there is a data set on one end, and that data set is converted into some modified form or mapped or transformed form of itself. Now, this is a big generalization. A lot of programmers won't feel that way, for example, when they're programming user interface, or if they're controlling machinery. That doesn't feel like they're transforming data. But in reality, they still are, because the user communicates with the program through input data received by the program. And any control or robotics is the same thing. The program will put data in a particular location, and that will be translated into a voltage which turns a motor on or off, and so on and so forth. Now, before we deal with real data, I thought it would be good to look at random data and just see a little bit about how computers and mathematicians working together end up characterizing data and analyzing data. And this is will be the focus of these first lessons. Will be data processing, right? All right, now we have some tools that I'm going to use. Over here, you can see that I have, well, I guess you've been looking at it the whole time, but what you're looking at is a Python notebook. Now, Python notebook is a useful way to use Python interactively, and you can also mark up the page so that there's cells in this page that run Python. You can see the Python in them now, and then there's cells that have what we call markup that are just rendered to document the page. All right, so we're going to create some random data here. And as I've written there, no data is totally random, right? If I make a list of random numbers between 1 and 10, the fact that these numbers are bound, constrained between 1 and 10 is a non-random constraint. If the numbers are limited to whole numbers, for example, or integers, that's further a constraint. You know, it's a limit on their randomness, and this is the element of the kind of randomness we're going to be talking about, and randomness as it happens in the real world, which is probabilism. So we're going to make a little set of data to play with, get an idea of how computers deal with real-world data by starting with random data. But we're also going to have under there a basic function. So basically, I'm going to create a data set that, for example, is a line, but it's plus or minus a random amount, or it's a parabola, but it's plus or minus a random amount. And I have a little program that can make it basically makes the function y equals x to the n. And we'll call n the order of the function, because we're going to be dealing with polynomials. So first of all, these are the cells here. I can number the lines. Usually I will number the lines. This first one just is going to do two things. This line, this Pylab inline, this is a so-called magic, and it just has to do with this notebook that I'm using, this web page interface. It imports a bunch of things for me all at once, having to do with plotting, so that we can look at the things that we've created. Now, NumPy, on the other hand, is a general Python add-on, the package or a library. You can import NumPy, and it's traditional to import it as NP. That means that I'll be able to refer to the NumPy module as NP in the later code. So I execute that. I had executed it before, so see it ran twice. That's what it says when it runs twice. Now here's the create dataset function we'll use to create some semi-random data, right? Data that's random but within some constraints. It follows a line or a parabola. It follows this function we'll create of some order, but then randomness or noise is added in. All right, so here's how you define a function in Python. And Python is the language I'll primarily be using, but we'll also get onto other languages. But Python is the language we'll be using for these lessons. And this is how we create our first Python function. We call it create dataset because it's going to create a dataset. And it takes a few arguments. One is the order, which defaults to 0. Now, if this defaults to 0, what does that mean? That means y equals x to the 0. That means y equals 1, because as we hopefully remember, anything to the power of 0 is 1. All right, rand is an argument to say either add or don't add the randomness to the function, which we will always be doing. And then there's the t-range. I don't want to call this range because that's a built-in function, but this is t-range. So this is the range of times or x-axis values, because we're going to be thinking of the x-axis as times, just to give it, you know, I don't know, some sort of a meaning. I could just be calling it the x's. And so what you see there is first of all, the list that those are the arguments, but then they're set equal to things. That means if the caller, the person calling this function, does not set these values, here are the defaults. So, for example, the default with t-range is -20 to 20. And let me just take a second and show you how that works. So if t-range equals this tuple, oops, got to be a comma, and we print t-range, it'll simply show us this tuple or this multiple pair. I can have called a tuple this data structure. I could, of course, have other elements to the tuple if I wanted. Okay, now with the tuple, it's a lot like a list or an array. So let's look at what the length of this will be, and of course it's going to be 2. Right. Now, how do I get those values out of the tuple? Well, just the same way I would for an array or a list. We use square brackets, and we give the integer indice, and I'll print that out, and we'll see that's -20. And if I print t-range 1, it's 20. Now, the print command by default, if you just separate things by commas, it'll put 1 space in between them. That's something to remember. There's other ways to control printing a lot better than that. And we want to remember, and this is important in programming, used to be a bigger deal, but we start our arrays or lists, whichever you want to call them, I'll use the terms interchangeably, with 0. So notice that a list of length 2 does not have an element of square bracket 2 because there's 0 and 1. All right. Okay, now I'll get rid of that cell. Now, here's what we're doing. First of all, we're going to have these times or x values. They're going to be set to a NumPy function called arange. Arange creates a list or a vector or a matrix, but it, just like the built-in array or square bracket data type in Python, but it does so very efficiently. So they can be huge. They can have millions of elements if you wanted to, and often do. And all of the number crunching and handling of these large data sets goes on in the NumPy extension, which is built in C. Therefore, you can do this very, very quick and optimized, even though you're using a scripting language, which of course is slower than a statically compiled language such as C or C++. So this function creates a one-dimensional a vector, which is just like a one-dimensional array in Python, and it takes the argument of what number you want it to start at and what number you want it end at, and then the increments for each number. So this takes t-range 0 and t-range 1, so that means this arange is going to be a list that goes from 2019, 18, 17, so far 0, 1, 2, 3, and up to 20, right? So it's going to be 41 elements long. But then this third argument says, well, what is the step size? So instead of using the default step size of 1, it's going to be of 0.5. So it's actually going to go 20, negative 19.5, negative 19, negative 18.5, and so on all the way up to 19.5, and then finally 20. So there'll be twice as many elements as that. And this is for our regular x values, which we want to go up at a steady rate. Now, d is the variable I just happen to have chosen for creating the y values, which, as I said, are going to be x to some power. Now, to do this in an efficient way, to multiply that vector by, or not to multiply, but take it to a power, so that element 10 in times in d, element 10 will be times to the given power. I use this power function in NP. It takes a vector, and then it takes a number, which I passed in here, and raises everything to that power. And of course, if the default comes in, it'll just be all ones. But if the order is 1, then it'll be y equals x. If the order is 2, it'll be y equals x squared. And it'll actually take the values from negative 20 to 20. Now here, I also want to create the randomized data. Right, so this is the regular data that's coming from a function, but then made discrete because we're just taking the values at these given times. So I'm going to make a copy of it because I want to modify it, but I want to save the original. So NumPy arrays called ND arrays are able to be copied. Then if rand means, well, if this flag is true, which it is by default, but it could be set to false, then for a range where I equals 0 to the length of the data, then for each element, remember at this point, everything in RD is the same as D. So RD of I equals d of I plus a random number from 0 to 1. This function gives a random number from 0 to 1 times that value, so some fraction of that value, right, minus half of that value, and that's so that it'll basically be equal to the value a random amount times the value centered midway in the value, right? So it might be a random amount negative, it might be a random amount positive, equal chance. Now I notice I put random here, so I actually need to import random. See, because I use random here, this random module that has a function that's also called random, I have to import that, so we'll import that again. All right, now, and then this function wants to return the data it's created, so it returns the times, the data, and the randomized data. Okay, so that just defines a function. We haven't actually created the data. To do that, we'll call the function. So here's how you call a function. And we'll tell it to create something of order 1. That means it'll be a line. It'll be y equals x. And it'll return us all those x values, the data, or y values corresponding to each x, and then the randomized data. Then we're just going to plot the randomized data. Now this is a function that comes in from that PyLab module. So when we call plot, we give it all the x's, and this is how it wants the data, all the randomized y values, the randomized data. This argument tells it how to mark it. We can mark this as a line or whatever. We're telling it to make circles. And then we're going to make the face color blue, but very transparent, right? So that's RGB. And then this is how transparent it is, or actually how opaque. So that's mostly transparent. And now we'll get a plot. Okay, so this is the data that we created, right? And see how it spreads up bigger and bigger, and that's because of this whole thing where I'm multiplying a random number times the number itself. So how much it spreads out increases as it gets further and further away from 0. That's the randomized data. Now let's look at the line that we created, this y equals x line, and plot that with the randomized dots and see how they compare. So this dashed line is the data calculated directly from the x equals y. And then these blue dots are the randomized data, which are all skewed off of that line. Okay, the way it was plotted is every time I call plot, it adds it to the same plot. Notebooks are smart enough that at the end, if I've ended with a plot, it'll know to draw it. So this says plot the times versus the RD with the O circles and the transparent color. And this one says plot the times versus the regular data with the color equals red and the line style dashed. Matplotlib is really awesome. All right, so the point here, though, is that we're going to try to fit the data, right? So we're going to use a polynomial. Now, here's a little writing about polynomials, and the thing is that a polynomial is an equation of the form, a to the n times x to the n plus a to the n minus 1 times x to the n minus 1 plus so on and so forth, right down to a to the 2x squared plus a to the 1 times x plus a to the 0. In other words, you can define these things in terms of all of these coefficients from a0 to a sub n, right? And they're always multiplied times an equation. So if I give in my little documentation here an example is 0.5x squared plus 2.2x plus 0.043. That would be a polynomial, and we would call that of order 2 because it goes up to x equals 2. Now, it turns out to be the fact that for any set of points, you can calculate a polynomial that will go through those points if you have an infinite number of terms, right? So if it goes up to x to the infinite. The thing is, you can do really well with just a few number of terms, 5, 10, 20, 50, right? So x to the 50 plus something times x to the 49 and so on and so forth. And NumPy knows how to do this. All right. Now, so this is what we're going to do, and let's look how it works. So first of all, we have some more to import from NumPy. We're going to import the polynomial module with the function polyfit from the polynomial module. So this says from the module NumPy, submodule polynomial, submodule polynomial, again, import the polyfit name, which happens to be a function. And from NumPy, we're also going to import poly1d for turning the coefficients back into a formula. All right. Now here is where we're going to ask for the num terms, and this is actually the order, right? Here we get the coefficients for the polynomial, in other words, the a sub n, by using n polyfit. Give it the times, these are the x values, give it the random data it's trying to fit, right? And then these number of terms, which is 1, or this is the order. Then we call fitPoly to create a polynomial object, a NumPy polynomial object, by calling poly1d with those coefficients, right? Then we create the poly_y by calling, what I'll call poly_y, by calling fitPoly to the times, right? So this was fitPoly, was the poly1d of the coefficients. Then we're going to make a poly that is the fitPoly of that times. This times is a long vector, right, with all of those times in it. So this returns a vector where fitPoly has been run on all of those times, and then you end up with another vector that's all of these new y values from your fit. You'll see what I mean in a second. Now here I have some control flags to say if I want to plot things, and I'm going to plot all 3 of these. I'm going to plot the data, right, and it's going to be the red dashed line. I'm going to plot the source, right? I'm sorry. I kind of made it confusing. I'm going to plot the data, which is actually the randomized data, which was simulating our input data, our measurements from the real world. I'm going to plot the source, which is the formulaic starting data that I've randomized, and that's the red dashed line. And then I'm going to plot the fit that the computer is fit to see what it thinks the formulaic relationship is between the data. All right. So there we get it. So the red dashed line is the y equals x line, and then there's all the randomized dots, and then the computer is able to fit this green line as its guess, trying to guess what the red dashed line was. Right. Now let's look at what that polynomial is. Now we know that the real original polynomial that got randomized was y equals x. This has y equals a little bit more than x, plus it's offset by a little bit of a negative offset. So got the line just a little bit off, which you can also see in the graph. Now next time I'm going to talk about the same page here, but we're going to up the order, and so I'll show you a little bit what's going to happen and see if you can understand what's going on. All right, so now we're going to make a second order data set where the data is all splayed out along a parabola. So that's what the randomized data is. That's what the randomized data is when it's plotted against the parabola that was randomized. Now if I do a fit of the data and I'm still at order 1, this green line is what it's estimating the line that data is along. By saying it was a first order phenomena, I'm saying it's going to be a line. Well, this actually is a second order phenomena. If I know that, I can go ahead and change the number of terms so that it's a second order, and there now it matches very closely. And that's because I knew that the data, I wanted to fit the data with the second order. Let's say I just wanted a really good fit. Let's say I put 12 terms. Okay, now the green line has more flexibility to follow that randomized data, and it's actually further off of what would be the natural phenomena behind this data, the red dashed line, the source phenomena. And just to look at what that is, that function here is what the result of it is, all of those coefficients, starting at x to the 12 because it was 12th order. Okay, and we'll look more at this kind of thing next time. All right, cheers.